you guys need with that. So, AP biology and thermodynamics. Looking at this, it's going to be pretty straightforward. Keep in mind that when we talk about thermodynamics in terms of a living system, what we're talking about really is their metabolism. And the map you see here in the purple is the total metabolism of an organism. I don't know which one, but every line indicates a transition. Every black dot is from one substance to another one. And so when we take all of this and we put it together, that is the metabolism. We talked about cellular respiration and photosynthesis in the last few days, practicing with those. So hopefully it doesn't surprise anybody to now see us moving into this concept of metabolism and how it works. So, first, let's start by talking and clarifying once more exactly what that energy is. Whether we're storing it into a stable molecule in photosynthesis or whether we are breaking it free from that storage for utilization in cellular respiration. Remember, the key for energy is its ability to do work. It has to be able to do some kind of work, and that work can take different flavors. We've got transport work, mechanical work, chemical work. So the difference between letting things move, physically moving things, or chemically putting things together, right? Any one of those could use that extra phosphorus in order to provide the energy that they need in order to accomplish it. This goes to reviewing just a little bit of more traditional physics with potential versus kinetic energy. Now, the important thing is to identify that when we're talking about kinetic energy, that's going to include heat. And when we're talking about potential energy, that's going to include chemical bonds. So, chemical potential energy. Those two things are really important and they help everything else to make a lot more sense. So, when we take a look at some chemical reaction occurring, what we're looking at the beginning is that chemical potential energy. And that is what ATP will ultimately generate is chemical potential energy that can then be released as kinetic energy for use. Now, when we take a look at these, you could take a look at all the different bonding that we see, the single bonds, the double bonds, and of course, these are all lines. So all of these are our normal covalent bonds. These are not ionic. We're not talking about necessarily hydrogen bonds or anything like that. And in this case, we're looking at two of our biological molecules, a carbohydrate, glucose, and a lipid, in this case, just fat. And if you are asked about something about the energy level between these, remember the energy level is going to be determined by kind of like the nature of the bonding, looking some at like the electrons that they need in their outer shell, things like that. The more electrons that are shared, and the stronger, the higher electronegativity difference that we see between these atoms. So if you take a look, the carbon to carbon bonds are obviously going to be the strongest ones, but they're actually too strong. They're way too strong for us to reasonably or easily break. And so what we tend to do is we tend to focus on that second one, our carbon hydrogen bonds, because they are the second most energy rich bond and they're an awful lot easier to break than the carbon ones. So they give us the best turnaround, the best reward for the amount of investment that we put into it. So I'm not going to spend a lot of time with thermodynamics, but hopefully you guys remember these from physics. The idea that energy is constant and we can change it, but we can't create it, we can't destroy it. Right? So the gas you put into your car has to be accounted for when that gas is burned. It's not like it just goes away. Now, the second law is our entropy. And remember, entropy is what the universe wants everything to get to. The best entropy energy that we have that you can think of really is heat. Heat is just lost, it just emanates out. That is what it is. Heat is the energy of entropy. And that is a lot of disarray. So when we take these two laws and we put them together, we get a relatively elegant and simple way to really work on it and think of it. But if you take this bear and by adding some of these labels, it makes it a little bit easier to think of. You can think of the food that's going in as the chemical energy, right? That's the chemical potential energy. And then when that is burned, we have to be able to account for it. Now, maybe we account for it as the products, the CO2, the H2O that is generated by cellular respiration, but we also can account for it as heat, which is actually where most of our energy goes after we have utilized or freed it. It is just expelled out into the universe around us. Now on this, I've included some questions for you. You are free to go back and use them for review, but I'm just going to roll onward. And so when we take a look at it, it's important to understand this idea of an open system. All right, if you're alive, you're an open system. And what that means is that not only do we have to take into account the laws of thermodynamics for how that's going to affect us, but we also need to take into account then the fact that we are working at a loss. We need to constantly be moving things into us in order to maintain life because we are losing energy out, that heat energy. We're losing that at every exchange. We utilize it to help keep ourselves warm, but ultimately it means that we are less effective than we could be. So you can think of a living thing as an island amid a sea of chaos, right? Like we are constantly working to maintain our own structure and organization and at the same point resist um, outside attempts to change or alter our organization. And this will bring us into our exergonic and endergonic again. So, taking a look at this first one, we see that one big molecule is turned into smaller pieces and energy. Would that be an exergonic or an endergonic reaction? Now, remember, try to use chemistry if you don't remember what these are, because a lot of that still works the same way. Yes, exergonic, because we are giving out energy, we're not taking it in. How can you tell? Well, I mean, energy is one of the products. Now, if we were attributing that to a change in Gibbs free energy, our delta G, would this be a negative G or a positive G? And I'm going to let you guys sit on that one for just a moment, and we're going to worry about that coming up. And then what about the opposite? What can we tell? With what we determined from the first example here, the opposite of it, where we have a lot of those little ones and energy coming together to make a larger molecule. So, is this going to release energy or absorb energy? And that's okay, man. You're catching up. This one's going to absorb energy from the environment. You can justify that by seeing that energy is required for this to happen. Now, which one would this be? Would this be cellular respiration or would this be photosynthesis? Why would this be photosynthesis? What's your reasoning? Well, let's take a look at it. Remember, photosynthesis is going to be taking the physical materials that we have, right, and it's going to be making that glucose. And here we see that we are reducing the amount of entropy, the amount of disorder, by taking energy and material and forming it into a new structure. That is definitely going to be a photosynthetic style reaction where we are generating something. In fact, the word synthesis means to make. So you can keep that in mind, and hopefully it would help a lot. The products have more or less free energy than the reactants. Well, hopefully you can identify that they're going to have less free energy. They're going to have more potential energy, but less free energy. So, and then here is the breakdown between those and the actual equations. Now, an interesting thing to note, and I want you guys to be aware of this, is if you don't remember, I had another meeting with College Board and the folks who are running this. And in it, they were going over what we could expect for the test and what we think things are going to look like. One of the things that they pointed out was that for chemistry and physics, you needed to have your equation sheet. For AP Bio, they could not answer whether or not we needed our equation sheet. I asked that in the chat, and they're like, "Oh, yeah, let's pass that over to the bio lead. Do you need your equation sheet?" And they couldn't answer. So I think that our equation sheet is going to be less important for this exam, given that there's only two questions. But they said that on the 28th, they're going to be having another one. So I will go to that one too, and with any luck, I'll have some more information or even more information after that to share with you guys. So this is all that Gibbs free energy equation. Now, you should then be able to take a look at these different states, the first state and then the second state, and identify which side, top or bottom, has more free energy, which side has less free energy, which has the higher and lower G values, the stability, the work. Like, I'm going to blip by this, but feel free to go back through and double check it. And then I included a review of your exergonic versus your endergonic, along with, once again, some stuff for you guys to include yourself. And remember, those exergonic reactions, the delta G, the change in G, is going to be below zero. It's going to be a negative change in G when it's releasing energy out, because it's making that energy available. It's not using it. Endergonic, when we do use it, that is going to have a delta G value of positive because we are now effectively removing it. And those numbers, the numericalness of it, has always distracted me. But this may help you guys kind of make sense out of it. Hopefully, at least the pictures will. All right, and then this was an example that was on the worksheet when I first found it, and I really liked it. So I just kept everything exactly as they had it. Uh, but I thought it was good to kind of explain the difference here. All right, so these are closed systems. And in the closed system, you've got one that's doing nothing, a delta G, a change in energy of zero, and another one that is generating energy, delta G of below zero, of a negative number. Right? And that's a closed system. What's important to note is that, remember, we are an open system. So we're far more like this second diagram. We need a constant supply of material coming in, and we will also be releasing a constant supply of material back out. So in order to keep this process going, you got to keep bringing things in, which is what all of us are really, really familiar with right now, because I don't know about you, but I've probably gained 5 pounds since we started this social distancing because every time I walk by that fridge, I'm reaching in there to grab something else that I don't need. The neckline on the shirts is getting a little tight. Right? Man, when you get bored, you just eat a lot. So keep this in mind. And then keep in mind that if we want to get some sort of equilibrium for this, that would be great, but we're not designed for equilibrium. We're designed to constantly be working at some kind of a loss and therefore needing things to constantly be added to us. It may seem bad to say something like disequilibrium on this, but it's not an incorrect statement because we are constantly not at equilibrium. If we were, we wouldn't need anything, but we always need to breathe. So we know that we're not at a good equilibrium. And then they included this picture for a catabolic pathway, which once again I think is really kind of nice to show not only that constant input and output, but then how each one of these reactions would be linked to the next one. Hopefully, you guys remember that when we were talking about energy. We were pointing out that almost all of these abilities that living systems have are always linked to another one. If one generates energy, we need another one to utilize that energy. If one needs to utilize that energy, we need to link it to one that's generating the energy. Because to have too much free energy just floating around in us is super bad, and the body does not work well with that. And then that can bring us back to that first diagram that we looked at with the different types of work and the description of how ATP can power each one of those. Um, they had this, and while I don't find it quite as useful, this is a picture of ATP, adenosine triphosphate, the phosphate groups over here in the red. And it's just sort of a diagram of how it's set up, what it means, and of course the phosphate tail being that energy important section of it. And then closing just with this idea, and once again, it's that linkage between the different types of reactions and the energy they either produce or consume. So it's a lot of stuff, it's really quick, but I wanted to review that before I see you guys tomorrow.